Hello everyone, welcome to my YouTube channel. Let's solve the fourth problem. Right, so the problem is every element occurs twice except one element. So you have to find the unique element which is occurring one time. They have also given the note duplicate elements are adjacent to each other but the array is not sorted. So they have also mentioned that the duplicate elements are always adjacent. Let's see the example to make it more clear. Let me quickly index it. So here you can see the adjacent elements are duplicate, adjacent elements are duplicate, adjacent element are duplicate. So one element which is not unique is 6. So the answer is 6. Adjacent element duplicate, adjacent element duplicate, adjacent element duplicate, duplicate, duplicate. Only one element which is not having duplicate. So that's why our answer is 3. Here also third question, adjacent duplicate, 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 duplicate. Here only 19 answer is appearing one time, so that is unique element, right? So I hope you understood the problem statement. You have to find the unique element. Now what can be the brute force approach to solve this problem? So one brute force approach that comes to my mind right now is, what we can do, we can create a frequency map, right? Or we can create a frequency map, or we can create a hash map, right? Now after creating a frequency map, what we can do, we can have a hash table having element and having number of times or count of the element, right? We can have a element and we can have a count of that element. So if the count is 1, then we will simply return the element, because that element will be the unique element, right? So you can create a frequency map, and if the count of that element is 1, then that element is the unique element, right? So now what is the time complexity of this approach? So the time complexity of this approach, we will traverse the array, so the time complexity is order of n. What is the space complexity of this approach? Because we have to store each element in the hash map, right? So the worst case, the space will be requiring n element we can store in the hash map. So that's why the time complexity is order of n, and space complexity is also order of n. So this is one approach. What can be the other approach to solve or to find the unique element? Another approach is we can use bit manipulation concept, right? We have already understood bit manipulation concept. So one approach is we can use XOR operation. We can do XOR of all array element, right? We will iterate the given array and we will apply XOR operation for all the array element. Now what is a XOR operation? Advantage of XOR operation: when two elements are identical, if we do XOR of two identical, it will cancel out each other, right? So this is cancelling out, 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 because they are same element, right? So XOR of same element is, it will cancel out each other, right? So the unique element here 19 will not cancel out each other, so it will return our unique element, right? So this is the another approach. We can traverse the, or we can iterate the given array and we will write XOR of all the array element, right? Now what is the time complexity? We are traversing the array one time, so the time complexity is order of n. We are not using any space, so that's why the space complexity is order of 1, right? So we have improved our brute force approach. In the brute force approach, the space complexity was using frequency map, the space complexity was order of n. But in the second approach, the space complexity reduces to order of n. And what can be other approach? So one approach that can be derived from the node they have mentioned, the duplicate elements are adjacent, right? So from this we can derive one normal approach, or one what we can say, one normal iteration. We can find the using the normal iteration. What we can do, as they have given that duplicate elements are adjacent, so we can write a check that if this element, if its adjacent elements are duplicate, then it is not a unique element. If this adjacent element are unique, it's not a unique element. If its adjacent element are unique, then it's not a unique element. If its adjacent elements are unique, then it's not a unique element, right? So what can do, we can check the adjacent pair. Let me write, we can check the adjacent pair, right? Since duplicates are adjacent to each other, that they have already given in the note, what we can do, we can write the condition: if array of I is not equal to array of I minus 1, the previous element, if it is not equal, then array of I is the unique element, because it is not equal, right? If because the condition or the note is saying that the duplicate elements are always adjacent. So if it is not adjacent, then array of I is the unique element, right? And we will iterate from I equal to 1, I is less than equal to n, I is less than n, and I plus equal to 2, because we are searching for adjacent pair. So that's why we will iterate I equal to I plus 2, right? Because we are checking the adjacent pair, right? So that's why, and we are starting I from 1 and ending to I less than n, right? So this can be the normal iteration approach. Now what is the edge case for this approach? What is the edge case? What if the first element is unique element, because there is no I minus 1? What if the last element is unique? There is no I minus 1, right? There is no next element. So for the first and the last occurrence, what we can do, we can check their duplicacy. We can check their duplicacy for first and last element separately, right? We can write two if condition, and then we can check it separately, right? So we have avoided our edge cases. Now what is the time complexity of this normal iteration approach? We are traversing the array, right? So time complexity is order of n. We are not using any space, so that's why space complexity is order of 1, right? So this is a third approach, right? But all the three approaches, we are using order of n space. For frequency map, order of n; for bit manipulation, order of n; and for normal iteration approach is also order of n. Can we further optimize this solution, or is there any optimized approach to solve this problem, right? So let's do some observation. Let's take an example. Let's take an example of array. Let's say the array given to us is 7 7 6 6, previous example only, 3 8 8 1 1 9 9. So this is the array given. Let me write the indexing: 0 1 2 3 4 5 6 7 8 9 10, right? So I have done the indexing. Now let's try to, because they have given in the note duplicate elements are adjacent, right? So here the element is coming 2 times, right? So let's do some identification, or let's identify the index of first occurrence, because we can identify the index of first occurrence of duplicate element or of all elements. Right, we can identify the, so what I'm saying is, element is given, we will see the index of first occurrence. When what is the index at which this element is coming? What is the first occurrence of that index, right? So in this element is 7, right? So element is 7. So what is the first occurrence of that element? Here in this array, 7 is coming 2 times, 7 at index 0, 7 at index 1. So what is first occurrence? It is not 1, it is 0, because 0 is the first occurrence. So the answer is 0. For 6, what is the first occurrence? For another element 6, what is the first occurrence? 2 and 3. First occurrence is 2. Second, next element 3. What is there is only one occurrence of the 3, that is at index 4. For 8 there are two occurrences. First occurrence is index 5. For 1 another element, what is the first occurrence? 7 and 8, so first occurrence is 7. For 9 element, what is the first occurrence? 9 and 10, so the first occurrence is 9, right? So let me write, so here for 7 elements 0 index is the first occurrence, then 0 is even. For 6 it is 2, so 2 is also even. For 3 it is 4, 4 is also even. For next element 8 it is 5, it is odd. For one element the first index occurrence is also odd. From 9 it is also odd, right? So, and what is the unique element here? We know that the unique element here is 3. 3 is the unique element, right? So can you see something? Can you derive conclusion after seeing this? So what can be the conclusion from this is, we can see that before we get the unique element, the index of first occurrence of element is even. But after we got the unique element, after unique element, the index of the first occurrence of element which is present in the array is odd, right? So before unique element, here 3 is the unique element, all the previous element is even, the first occurrence is even, and after we are getting the unique element, all the next element occurrence is odd, right? So this conclusion we can derive from this example, right? So can we apply binary search here? Can we apply? So for binary search, what we know? For binary search we need two things, right? For binary search what we need? We need target. So for this example, what is the target? We have to find the unique element, so the target is unique element. And second thing that we need is search space, right? So search space is our entire array from 0 to n-1. So let's dry run to check whether we can apply binary search here or not, right? Let me take another example and we will do the dry run and check whether we can apply binary search in this example or not. Let me take another example. 3 3 1 1 8 8 10 10 19 6 6 2 2 4 4, right? So I have taken bigger array so that we can do good dry run. Let me do indexing. 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14, right? So for binary search what we need two pointer, low pointer and high pointer, right? For dry run also we need two pointer, low, high, low, high, mid, first index occurrence, what is the status, whether it is even or odd, and then final is the action that we need to take, right? So let me draw the table and we will do the entire dry run for this example, right? So here the edge case is, what if the first element is the unique element and what if the last element is unique element, right? So for edge cases we will handle these edge cases separately, right? So first element, we will not for our iteration, for our dry run, we will not consider the first element and the last element, because we will handle that separately. That is the edge case for this problem statement, right? So we will start our low pointer from first index. So this is our low, this is our high, right? So the value of low is 1, and the value of the index of low is 1, and the index of high is 13. So what is the middle element? 1 plus 13 by 2, which is nothing but 7. Now at index 7, what is the element present? The element present is 10. So this is our middle element. So this, what is the first occurrence of the element 10? First occurrence of the element 10 is, what is the index? It is 6, right? Now 6 is even or odd? That status we have to write. So the 6 is even, so that's why it is the status they have shown is even. Now when it is even, what action should we take, right? As we have derived from this conclusion that if the element is unique, or if the element is unique, then it is even, right? When there is change, when we are traversing the array, and if we are getting even, that means we have not encountered the unique element, right? So if we have not encountered the unique element, then we have to move towards right to encounter it, right? So that's why what action we will take when the status is even, we will move towards right, because till now we have not reached the unique element. So we will move towards right, and to move towards right, what we need to update our low pointer. Low will be mid plus 1. So the mid is 7 plus 1. So updated low pointer will be 8, high will be 13. So 8 plus 13 by 2, which is 21 by 2, which is nothing but 10, right? So the middle value is now 10. Middle value index is 10. So at index 10, which element is present? It is 6 present. What is the first occurrence of this element? It is 9. So here it is 9. So this 9 is even or odd? It is odd, right? So we will write this status is odd. So when the status is odd, that means when we are here, that is when the middle element is here, before we have encountered the unique element, right? Because that's why the status become odd, right? As we have seen in this example. So if the first occurrence of an element will become odd, then we have encountered unique element previously, right? So that's why what we can do, we can, so if the status is odd, then that means we have already encountered unique element, and that unique element is present in the left side. So what we'll do, what action we will take, we will move towards left. We'll move towards left side. So to move towards left side, we have to update our high pointer. So high will be mid minus 1, right? So that's because because it is status is odd, so that we have already encountered unique element. So we'll move towards left side, right? So the low pointer is not updated, so it is 8. High pointer is mid minus 1. So mid is 10. 10 minus 1, it is 9. So 8 plus 9, 8 plus 9, 8 plus 9 by 2, which is 17 by 2, which is 8, right? So middle element will be now 8. So 8 is the middle element. What is the element present at the index 8? It is 19. What is the first occurrence of that element? What is the index of first occurrence of that element? It is 8. And what is the status? 8 is even or odd? 8 is even. So we will write even. So if the status is even, what we have to do, we have to move towards right, because we have not encountered unique element. We will move towards right. So to move towards right, what we have to do, we have to update our low pointer. So low pointer will be mid plus 1. So mid is 8. 8 plus 1, 9. So low pointer is 9. High pointer is 9. right? And so that means we have ended the loop, right? Low, if low is less than equal to high, so we can stop the loop, right? And from also, I think this iteration is even not required. Now 8 is the unique element, right, that we have to search, because in this array, what is the unique element that we wanted to search? It was nothing but 19, right? So here also we can stop the loop, right? So this is how we can solve this problem, right? So this is how we can apply binary search for this example. Similarly, we can apply binary search for other example. I hope you understood this dry run, right? So we can solve this, example for the dry run, right? Now let me quickly write the condition for checking the unique element. So what is the condition that I have written for checking the unique element? Let me write the condition. So what is the condition? The condition is if array of mid minus 1 is not equal to array of mid and array of mid is not equal to array of mid plus 1, then that means the array of mid is unique element, right? So this condition we have applied here, and that's why we got, right? Because see, we have for this array, the previous element and the next element was not unique, right? So that's why we have stopped the loop, right? So this was the condition for checking the unique element. So we'll apply this condition to check the unique element. Understood? So I hope you understood this dry run. Let me quickly write the code how we can solve this problem. Let's quickly write the code, right? So let's define the function find unique from duplicate. And we are taking an array as parameter, right? Now I have told you for this array, or for using a binary search, what we'll do for the first element and for the last element, we'll write the separate condition, right? So what we'll do, we will check if first and last is unique or not. We will handle them separately. So we have to just write two if condition. If array of 0 is not equal to array of 1. So if this is true, then what we will do, we will simply return array of 0, because array of 0 is the unique element. This is for first element. Now for last element, what we'll do, if array of n minus 1 is not equal to array of n minus 2, that means then we will simply return array of n minus 1, because last element is the unique element, right? So this is how we have handled the first and the last element check, right? Now let's write the logic of binary search. We will take two pointer. Low will start from 1, high we will start from n minus 2. We will write the same binary search approach. While low is less than equal to high, we will calculate mid. So the formula to calculate mid is low plus high minus low by 2. Again we will write the condition for checking the unique element. This condition I have to write, condition for checking the unique element. What is the condition? If array of mid minus 1 is not equal to array of mid and array of mid is not equal to array of mid plus 1, then that means we will simply return array of mid, because that is the unique element, right? So now what we will do, we will now for this iteration, what was the thing, we have to calculate or we have to find the first occurrence. So how to find the first occurrence? For that we can write a separate function to find the first occurrence. Okay, so we can write a separate function for find index of first occurrence of array of mid that we are getting, right? So we can write a separate function, right? We can write a separate function. Let's say the function name is first index. Let me write it more clearly. Let's say the function is first index. This function, we will calculate the first index, we will take array and we will take middle. Two parameter we will take. We will store that into a variable called fi, right? Now if fi modulus 2 is equal to 0, that means, what does that mean? That means the first index of that occurrence is even, right? That means fi is even. So if the status is even, so that we have to move towards right? For this diagram, if the status is even, we have to move towards right. So which pointer we have to update? We have to update low pointer, right? So what we'll do, low will be mid plus 1, because unique element is in right side. Else that means f of I is odd. So if fi, that means fi is odd. So if fi is odd, then our unique element is in left side. So if the unique element is in left side, then we have to update our high pointer. So high will be mid minus 1, right? So this is how we can find the index of first occurrence, and we will end our while loop. Let's say if the element is not present, then we will return -1 and the function is completed. So the function for calculating unique element from duplicate is ended here. Now let's write the logic for finding the first index. So let's write that function as well. So integer first index, that logic is very simple. It is taking array and it is taking the middle element, right? The logic is simple, only if one if condition is there. If the array of mid is equal to array of mid plus 1, if this condition is true, that means what we'll do, we will simply return the middle element, because that is the first index, right? Else we will return mid plus 1, because if it is not similar, then mid minus 1 is the first occurrence. Mid minus 1, not mid plus 1. Okay, so this is the logic for calculating the first index that we have used in this function here, right? So this is how you can write the code for finding unique element from duplicate using binary search. Approach. Now let's quickly see what is the time complexity and space complexity of this approach. So here we are using binary search. So what is the time complexity of binary search? Meaning the time complexity of binary search is log n, and space complexity is order of 1. We are not using any space. So this is the final optimized approach for this problem, right? The previous 3 approaches first was the frequency map approach. It is taking order of n time complexity. Bit manipulation taking order of n time complexity. Normal iteration taking order of n time complexity. But using binary search, We have reduced our time complexity from order of n to log n. I hope you understood this problem statement, right? Or I hope you understood the solution as well. So thank you for listening.